Okay, so we're going to be looking at chapter 4, section 4. That's root functions. That'll be a last section that we do. It's a pretty quick one. So in this section, we'll be looking at odd and even root functions, and we'll be looking at the different properties that they have. So to start, we have to define a root function. So a root function is of the form x to the power 1 over n. So we've seen a couple of these already. For example, x to the 1/2, which is the same thing as square root x. We've seen this already. We've probably dealt with x to the 1/3. That's the cube root. X to the 1/4. That's the fourth root. So this is a common way of seeing it with the actual root symbol. But for our purposes, and the purposes especially in calculus, the form where you actually write out the power is pretty beneficial. So we're going to go back and forth between them, but we really should get used to this top form. Okay, so first case, n is an even number. So again, remember, we're dealing with this or this. So when I reference n, I'm talking about that n or that n. So if n is even, 2, 4, 6, we get this picture. So there's a couple things we should think about in this picture, things we should pay attention to. So a couple points. For example, here is a point. This is 1, 1, and it looks like all three of our examples go through that point. So that's one we want to hold on to. Another one is right there, 0, 0. It looks like every one of our functions hits that point. And these are things that you can check, and I'm telling you that n even and n odd are the two separating cases. So then what you can do if you want is just hold on to an example. So square root of x, if you want that as kind of your base example, you could just try plugging stuff into that. So let's let x equal 0. Well, then the square root of 0 is 0. So I should see 0, 0 on the graph, and I do. Square root of 1, well, that's 1. Well, I should see 1, 1 on the graph, and again, I do. So that's pretty nice. It's something that you can just hold on to, those 2 points being on any of your even root functions. Okay, the next example is odd, so that's 3, 5, 7. Keep going. We see 3 points on here that are important. So here's 0, 0, here's 1, 1, and here's -1, -1. So these 3 points are really nice points that we can use when we're talking about odd root functions. Alright, so let's put everything together that we could see from those pictures. So for any root function, we noticed that 0, 0 is a common point, and 1, 1 is a common point. We also noticed for all the odd ones we looked at, -1, -1 was a common point. We should notice that back in the picture, for the even root functions, our picture stopped at 0. There were no input values for x that were less than 0. So something we could write down then is the domain is only 0 to infinity, where here for odd, the domain is -infinity to infinity. So interesting pieces we can kind of think about. We can also talk about the long run behavior. So as x gets really big, both odd and even root functions will go to infinity. The change, of course, is for an odd root function. We can go to big negative numbers, and we see that the function goes to -infinity. So if we go back a step, what I'm saying here is as x gets really big, we should notice that our functions are going off to infinity, and for odd we do. As x gets really big but small, negative, then we should see our functions going down towards -infinity. If we take one more step back, again, as x gets really big and positive, we see that our functions are going off to infinity. Okay. All right, so that gives us an idea for all of these functions. The next thing we're going to want to do is try to apply this to transformed versions. So here's an example of a transformed root function. So step one of this is identify even or odd. Since there's no number right here, that means that it's a square root. So square root, well, that's to the 1/2 power, so that's an even root. Okay, so then that means we're going to have a restricted domain. So remember, to start this off, you can always start with your base function where the domain is 0 to infinity, and then we'll build from there. So we should think about this for just a second. The domain of the square root function is 0 to infinity because the inside needs to be 0 or positive. So then all we have to do is apply that to our function. So we take our function and we say the inside needs to be 0 or positive. So write that. The inside needs to be 0 or positive. And then we can just solve for x. So I'm going to move some stuff over. I'm going to divide by 2. And we found our domain. We are allowed to plug in 2 or anything smaller than 2. So to rewrite that, our domain would be negative infinity up to 2. Or you could say x is less than or equal to 2. So that's our domain for this function. We'll check all of this later on a graph, so just hold on to that now. But we can always graph these things, so don't forget that. Okay, what's the range going to be? Well, there's a lot of pieces that actually go into this. If we're just thinking square root again, right, then we go back to the picture of the square root function, and at 0 it was 0, and then increased after that. So the range of this function is 0 to infinity. So then our only question is, what could change the range? Well, a vertical shift could do that. Some kind of flip across one of the axes could change this. You know, there's a couple of pieces for this specific example that something could happen there. So then we just look at what we have. We go to our function and we say, was there a vertical shift we have to deal with? And the answer to that is no, because remember, a vertical shift is adding or subtracting outside the function. We don't have that. All of our changes are inside the function. But we should say to ourselves, okay, well, what has happened to this function? Well, if we think about what's happening here, there is a subtraction side inside the function, which means there is definitely a horizontal shift going on. So definitely a horizontal shift. There's a multiple on the x, so that 2 there is being multiplied to the x. That means there is a horizontal, and we have to think about this. Is this a compression or a stretch? Well, remember 2 on the inside, that's bigger than 1. If it was vertical on the outside, we would think that's a stretch, but because it's on the inside, a 2 means it's a compress. Okay, but then there's one other piece. There's a negative sign right here. The negative sign means that we flipped across one of the axes. Okay, so which one did we flip across? So that's the thing we have to try to remember, right? We either went this way or we flipped over that way. So that's something we have to remember about transformations. Now, if I flip across the x, that means all of my y values become negative. My outputs become negative. So remember, that type of flip is I put a negative on the outside. Okay, if I flip across the y-axis, that means that my positive inputs now become my negative inputs. And so that should look a lot like putting a negative on the inside. So since we have a negative on the inside, it means we definitely took our function and we flipped it across the axis, the y-axis to be specific. All right, and so what we can do is we could just think about that in terms of our base picture. So we have this base picture we're going to draw over here. Okay, so then square root of x, we know hits 0, 0, 1, 1, and it continues on like this. Right? But you're telling me that there's a negative on the inside, which means I had to have flipped this over the y-axis, which means my picture really now looks something like this. Now we did more to it, so it's not going to be exactly that, because remember there is a shift. But we do know that that will be the general shape of it. Okay, and that's going to change a couple things that we have to think about. We should also say to ourselves, that means that my domain is now going to include a bunch of negatives, and we might be cutting off some of the positives. And you should look up to the domain now, all the way up here, and that should match. We took on all the way out to negative infinity. The other thing that helps you with the domain now is the domain doesn't just stop at 0, it actually goes all the way to 2. What that's telling me is that my picture actually should be shifted over by 2. How could we see that from the function that we have? Well, if we look at our function, I'm going to rewrite this slightly differently. I see a 2 in each of the 4 and 2, so I'm going to factor a 2 out. And there we go. We see, if we look in here, that this has a shift of 2. All right. So what is that shift of 2? Well, if we're going from 0, 0 as our point, that was right here, and we're moving it over to 2, that means that's a shift to the right of 2. All right. Okay, so then how could you try to see that? Well, it doesn't look like a minus 2 over here, but we could rewrite this. Here's a negative 2, x minus 2. So all I did was take a negative out of that 2 minus x piece. Okay, so then if I look here, I see, hey look, a shift to the right of 2, x minus 2. So that's perfect, I've got that. Okay, then I see this 2 in here is my horizontal compression, and this minus piece is my flipping over the axis. So my guess now from all this information is going to be that my picture, 1, 2, starts here and will take itself to the left and up towards infinity. Now what I can do, which is actually pretty nice with these, is then I could just ask myself, well, what's one other point that's really nice? Well, one point that would be nice for this picture would be to ask, okay, where is the y-intercept? So remember, y-intercept happens when x is equal to 0. So we just plug that into our function, 4 minus 2 times 0. That gives us square root of 4, which is 2. So 1, 2. Here's my other point, and there's my function. Now, the exact shape of the function, we haven't actually considered the compression, and that'll change the shape, of course, but this is a pretty good picture, and this would be really the most I could ask you to do for a problem like this. So just to kind of think about what we did here, we checked out the domain, we got that, we looked at what was happening to this function. There was a shift, a compression, and a flip across the y-axis. We noticed that we could figure out the x and y intercepts by just either algebraically doing them, or we kind of use the domain and some of our thinking about transformations to also find the x-intercept. So lots of options here, ways you can do this, but this would be pretty good. And just to kind of sum things up then, our range in this case would be, we still start at 0. That's the lowest our y value gets, and we go off to infinity. So there you go. All right, so let's try another one. So let's do the same stuff for this function. So what we should do is just try to write as much as we possibly can about this before we start. So first thing I notice is here's a 4. This means that this is even. Okay. Now, what I could do if I wanted to is just write everything down I know about even root functions to start. We have to think about what changes here, but we can at least start at a point where we know a lot. So an even, just basic even, will go 0, 0. It'll hit 1, 1. As x goes to infinity, the function goes to infinity. And we've got a ton of info there. So then what we have to do is think about, well, what happens? What's different? Well, the only thing I see here is this -3. So this is on the outside of the function, which means it's a vertical stretch by 3. And then remember, the minus sign means a minus on the outside is going to flip me over the x-axis. So what I should do when I see an even root function is I can just draw myself a nice picture. All right, there's my even root function, and think about what happens. Well, I know that the minus sign is going to take me across the axis. So the minus means I'm going to go across the axis here. Okay. And then the 3, I just have to think about what happens here. So one thing I could do is I could just look at the points that I know. I know this point and I know this point. I'll just kind of see what happens. You could just plug in the same x values and see what happens, or you could think about what's going to happen. So if I take my 1, 1, so let's take the 1, 1 here. That's, let's just say here, here. So that's my 1, 1, right? I'm going to negative flip it down. Oops, got rid of it. So I'm going to negative flip it down to this point, and then the 3 is going to multiply it by 3, which means I'm really going to be dropping, I'm really going to be dropping all the way down 1, 2, 3 to this point. So we can try to draw that in. So it's going to drop it all the way down here. Okay. So then we know about this new function, things that we know. Well, as x goes to infinity, now the function itself is going to negative infinity. That's because of that minus sign. We know we hit the point 0, 0. If I just plug 0 into this, if x equals 0, I'm going to get -3 times the 4th root of 0. Well, that's just 0. And then I know when I plug 1 in, I'm going to get to -3. And you can either do that via the transformations, or you can just try it. -3, 4th root of 1 is -3. Okay, so that's a ton of info. The domain of this, now we should think about this for a second. Did anything happen to the inside of the function? No. So the domain should stay exactly the same as the base 4th root function. The range now, just kind of looking at it, it's still, again, I'm looking at the purple. Now the biggest value I get to is 0, and it shoots off to negative infinity. So I've got my range, I've got my long run behavior, I've got some nice points, and I'm good to go. So go look at this section. They do a couple more examples that are similar to this. Again, if I ever give you anything like this on a quiz or a test, well, we got no more quizzes, just the final. I'll give you really nice points if I'm going to give you a graph, or I'll give you a very reasonable formula to investigate. But it's going to be up to you whether you want to do this all algebraically, if you want to use transformations. You're just going to have to put everything you know together to solve problems like this. The end.